It's time!
Time for what, ma'am?
It's time to have an idea about time dilation. But before we tackle about time dilation, let's first understand the first and second postulate of special relativity.
Ma'am, the first postulate is the idea that the laws of physics are the same and can be stated in their simplest form in all inertial frames of reference. Whether you are standing still with respect to Earth or in constant motion, the laws of physics will always apply the same.
Very well said. About the second postulate of special relativity, it is the idea that the speed of light c is a constant independent of the relative motion of the source. Let's compare the speed of light to a car. If you are stationary to the ground and you measure a speed of a car going 50 kilometers per hour, the detector will read 50 kilometers per hour. If you are moving 30 kilometers per hour and a car passes you going 50 kilometers per hour, you will measure the speed of the car as 20 kilometers per hour because it only moves 20 kilometers per hour relative to you. But light doesn't work the same like the car. Whether you're standing still, moving along with it, or going to the opposite direction, it will always be 300 million meters per second. Let's get now to the main topic on how speed affects time using mirrors. Imagine two mirrors facing each other, 1 meter apart. It will take 2/c of a second for the light to travel the other side and back.
How about, ma'am, let's compare it to two mirrors, facing also each other 1 meter apart. But this time, those two mirrors was mounted into a spaceship, traveling in a tremendous speed. Do you think the photon will travel at the same time compared to the stationary one?
The answer will depend on the inertial frame of reference. To the Earth observer, the photon has traveled diagonally, so the light has to travel a longer distance, therefore longer time and slower vertical motion.
But here's the interesting part, ma'am. Let us look on the perspective of the person inside the spacecraft. If the light traveled diagonally, slowing the vertical motion, we can assume that the light traveled vertically slower pace relative to the astronaut, right?
No, as we discussed earlier, light is always traveling in constant speed no matter the frame of reference, so his perspective will be different as compared to the stationary. The light will still travel 300 million meters per second.
So if the astronaut sees the light traveling at sea vertically, but the Earth observer sees the light travel in a slow pace vertically, what made them arrive in a different conclusion?
The only reasonable explanation is the dilation of time.
The astronaut's time was slower, not only the photon clock and the detector, but also his biological clock, like heart, lungs, brain, and everything with him got slower. So in his perspective, the light still travels as the same as they were stationary. We can compare the amount of time by showing you this difference time interval. To the left, we can see what the astronaut perceived the motion of light, which is delta t0, and to the right, we can see that the Earth observer perceived, which is delta t. We can observe that the time has dilated or expanded relative to delta t0. As a result, the clock on the spaceship is running more slowly.
Wow, Therese, you really have an idea. I have nothing to say.